Swayam Prabha. Digital India. Educated India.
Good morning, everyone. It is truly a pleasure to welcome back Professor Avishek Chaterjee. Your previous session left us inspired and curious, and we are delighted to have the opportunity to learn from you again today. We look forward to another insightful and engaging lecture. On behalf of everyone present here, I extend a warm welcome to you, sir.
Okay, so if you remember what we talked about last time, I give you some idea about computation in the presence of errors. The motivation was there are certain futuristic computation techniques which will be noisy but very fast. So can you exploit the fast behavior despite being it noisy, can you make it accurate and fast? So that is one aspect we discussed. And one motivation we said was what kind of computation? It's in news. So anyone remembers? It's quantum computation. Okay. So this is something that's gonna be a future technology. There we tried to understand that. Okay. So we had two lectures. First lecture I talked about that mostly. Then in the second lecture we talked about how opinions spread on social networks. So I think the title was Who Told Whom. Like if some message is spreading, suppose in a school network, you want to form a team or you want to reach a consensus about for your school fest, which artist to call. So how does that reach and how do you figure out who were most influential in making that decision? Okay. So that's what we discussed about. And your friends Harini, Riya, where is Riya? Riya and Grakesh, where is Grakesh? Oh, yes. They are trying to extend that to kind of a simple caricature setup where to figure out who told whom. Like they are kind of playing a game between them. So its idea is Harini and Riya, or Harini and Grakesh is trying to influence Riya. Two of them try to influence the third person. And I will just see what they are saying. By that, can I figure out who is influencing whom? Who is the influencer and who is the influenced? Can I figure that out? Okay. So why did we study that? One motivation was, you all know about influencer culture these days, right? People go on YouTube or Instagram, try to influence. Now suppose I know there is an influencer who talks about sports, like cricket, who talks about cricket. And I am a company who makes cricket equipments. You heard of SG, the Indian company which makes equipments, who sponsors Ravichandran Ashwin, Rahul Dravid, all these people. So suppose I have to figure out who are the real influencers in the cricket sense on YouTube. Why? Because if I know the guys, I'll go and pay them. Say that you talk about SG so that people buy more SG. So that's very beneficial for me as a company. So that's why I want to know it. Similarly for any other product, like somebody is talking about fitness. And there are a lot of fitness equipment, food and all. I have to figure out who is the influencer in fitness and try to say that, okay, talk something about my product. I'll give you some free products, talk about my product. So that's very important. And there is a very practical other use also, like the negative side which you want to prevent. Is suppose somebody is creating a false rumor about some bad things, like they're spreading some really malevolent intentions to destabilize our national security or something. You want to figure out who is doing that so that the government organizations can go and stop them, don't do it, or put them in jail if they don't listen. So both reasons are there. So that's one reason we are studying that. Now today we'll also look at that same thing, similar thing, but with a slight twist. Okay, it's a slight twist, and it's a slightly different from what Harini, Riya and Grakesh were working on. So let's see. Let's start from the beginning and let's see. I am just interested in the following, that suppose there are friends, okay. Friends form a network. What is this network? Just to remind us, is it visible? Madam, last you can see it, okay. So this is called social network. See, all of you know by now what is a social network, because you are all some or other way you are using it. It's just a friendship graph. So for example, this is person A, this is person B, person C. So what the connection means, that A is friend with both B and C, but B and C may not be friends. Okay. Similarly, there is a D, there is a E. Now B is friends with A, D and E, but A, D are not friends, A and D are not friends, but D and E are friends. Okay. So it can happen, right? You have this friend circle, you have 10 best friends, and among your best friends, they may not be friends. So suppose you have 10 best friends, okay. It's not necessarily all 10 are friends among each other, right? It can happen, cannot happen. So if I take you and your friends, so what I'll do, I'll take you, suppose you are A, I'll take you and all your friends and draw this picture and connect you with these lines. So this is a graph, and these guys are called nodes of a graph. We discussed it last time, but I'm just refreshing. And this connection, when I have a connection, I call it either a link, or it's also called edge. That kind of signifies friendship. Okay. So I suppose I go to any of your school, I take one person and figure out his or her friends, take one more, figure out his or her friends. Now I match them, I kind of connect them, I'll get this graph. Like whole school will be the nodes on the graph, and whoever are friends, I'll put an edge between them. So think of, I've collected all of your school students, put them on these nodes of the graph, and whenever two guys are friends, I put an edge. So that's called the social network or the social graph. You can also call it social graph. Okay. Now today we'll study, so last time we talked about how a particular thing is being spread. Like for example, you want to decide whom to call for your next music fest. Okay, I don't know what's the best musician for you. Means I am a very old guy, so I only remember Shankar Mahadevan, A.R. Rahman, maybe somebody else now, I don't know. Young, whoever. Suppose you're speaking between two musicians and you talk to each other and reach a consensus whom to call. Okay. So that's one thing. How do you do that? That suppose this guy says, I'll go for A.R. Rahman. And this guy says, no, I'll go for Shankar Mahadevan. So this guy I can call it 1, which is A.R. Rahman, and Shankar Rahman is 0. Or something like that. And things get spread. Maybe this guy gets influenced and he also says 1. Maybe this guy says, no, between this and this influence, I am more influenced by this. Says 0. So it spreads. So once it spreads, you will have a pattern of 1 and 0 on this thing. So depending on if you have more 1 or more 0, school will decide to call either this musician or that musician. Now here what Grakesh, Harini and Riya are working on is, suppose this discussion is going on for many days, not just one day. Okay, what I am talking about is just one instant, like they talk and decide. Suppose this discussion, because school fest is a big deal, we want to discuss for a month. So this discussion is going for long time. In this whole discussion process, maybe 1 or 2 persons or maybe 5 persons will be very influential, who will kind of convince everyone. So can I figure that out, who is doing that? Okay. So that's one approach. Okay. Fine. So one approach is, there is a choice. Nodes. I am calling it nodes. discuss. Question is, who influences whom? And you have to figure that out. Find just from the discussion outputs or just from the discussions. Can you find it out? Who influenced whom? Who is the influencer? Okay. This is something they will talk about. I think June 2nd. When is the June 2nd, right? When is it? June 2nd. So they will talk about it. So I won't repeat it because you will hear from them. Okay. But today we will talk about slightly different problem, very closely related. Suppose there is a news to be spread. News to be spread in the sense that suppose something happened that your midterm date, I don't know, was it called in school, class test or midterms. Suppose suddenly because of something your midterm date got changed. Okay. And suppose it's right after vacation, summer vacation, the day, right after the day summer vacation, there is a new midterm. Because you are not in school, your teachers can let you know. Okay. So how it spread? Teachers can call every one of your parents and let you know that, I don't know, 5,000, 6,000 students in school. It's a very hard job to call everyone and let them know that the midterm has changed. So one option is, what teacher does is, a very good option is, she knows her class. Okay, suppose in her class, she is a class teacher, she knows 30 of them and messages 30 parents saying midterm has changed. Can you share with the people you know? So they do that. Now, this is a very efficient way of spreading news. So now you see, this is not a little slightly different from influencing. You see, here, all people know A.R. Rahman, all people know Shankar Mahadevan. They are just trying to reach a consensus by discussing. Here, it's a totally different thing. It's like they do not even know this news. So the idea is to spread the news. Once you spread, it's done. There is no competition. Here, there is a competition. So, just to put here, there is a competing influence. Competition. 1 versus 0. This is an important thing. Somebody is trying to convince you 1, other person is trying to convince you 0. So, it's a competition. And information is already known. The scenario I am talking about, there is no competition. It's just you did not know that that news exists. So, it's just reaching you through different persons. Is the part clear? So, the next part is spread of information. So, here there is no competition. The information will just spread. So, how will it happen? So, there is this graph. Again, the graph is there. Now, this graph is not exactly that graph. This graph in this example is the graph of your parents. That was you, all of your friends. This is like because your teacher is texting your parents and your parents only have access to mobiles. So, it's like spreading among your parents. This is a different graph, but very similar in nature. It's like which parents are friends with which other parents. Here, which students are friends with which other students. Generally, they are similar looking but not exactly the same. It may be that your parents are friends with some other parents and that kid may not be your very good friend. But okay, may or may not be, not necessarily. So, they are related but not exactly. But nevertheless, it's a graph. So, the opinions, so suppose in this graph, there are teachers also. Because teacher is the one who influences, suppose this is the whole thing is the class. I don't know, whatever is called, class 11A or something, or B, whatever. This is the class. Teacher shares with the information with all of them. Now, they will share with their friends. First, they say, push it to all the friends. All the friends. Now, what happens here? When it pushes, so this is, suppose the place got information, I will call it I. I means it got information. So it pushes and it figures out these guys also have the information, these also have information because they are in the same class, but this does not. So this now becomes I. Now what happens? Now this person and this person, they all try to spread. What happens? It tries to spread to this. It tries to spread to this. So this becomes I, and then this becomes I, and so on. It goes on. Okay. So if you see, there's a very interesting thing happening here. Will everybody get the information eventually? I am not talking about 5 minutes or 10 minutes. Will reach eventually it will reach to everyone? It will reach to everyone. But there is a condition. Very good. So if no isolated nodes, it reaches everyone. So this is very important. It's intuitive, because if some node was there and not connected to anyone, not friend with any friend, any other person, that person won't get the information. So that's kind of a problem with this system. Okay. But generally it does not happen. Everybody has some friend in the world. Okay. So it will reach. Okay, everyone? Now, this is a very simple looking thing, but things can be little complicated. Things can be little complicated in the sense that the example I took was a quite harmless example, in the sense it's a midterm or no midterm coming from a parent, finally coming from a teacher. So it's a very reliable information. So there is no doubt about the information. If a teacher sent a message saying there is a midterm on someday, there is no doubt about it. It's not a prank. It cannot be a prank. A teacher won't prank a parent. Okay. It does not happen. So then there is no unreliability in it. Okay. So then everybody trusts the information and the information moves on. Now think of a scenario where it could be it's serious or maybe prank. It's like your WhatsApp forwards. Like random WhatsApp forwards, not necessarily coming from a teacher, but suppose, think of somebody spreads the information saying, oh, from tomorrow there is some big Ebola virus breakout or something. Okay. Somebody says. Now it may be true, may not be true. How do you know? Okay. You will trust only if the person is trustworthy. And sometimes even the trustworthy person may be duped by a different source and the person may forward a wrong message. It happens. You talk, I know you guys don't use WhatsApp, whoever uses WhatsApp, that happens all the time. Sometimes wrong messages get forwarded or not trustworthy. So that means what will happen there? Now, this scenario is, there is the graph, information starts from somewhere here. Now when it's spreading, there are two questions. So this guy here is asking two questions. Trust or not? Okay, so now there is a slight twist to the story. Here everything was trusted. Here there is full trust. Here the question is trust or don't trust. Okay. So that's a That's the new twist. Now suppose here we saw eventually it will reach everyone unless there is an isolated node. So let's forget about the isolated node condition because we know that's a corner case. Let's ignore it. Suppose there is no isolated node. So the question is no isolated node. Now the question is, can it reach all? There it was intuitive. If there are no isolated nodes, it will definitely reach all the information. Now the question is, there are isolated nodes. Sorry, there is no isolated nodes. But there is this new issue which is trust or not. This is a very, very important twist. So this is the new twist. Under this condition, you are asking, can it reach all? Will everybody get the information? Very good. So it's a very good point. See what will happen. Suppose the information starts from here. Now, if both of them do not trust it, that's the end of it. There is nothing will go. Fine? But suppose they trust it. Suppose I tell you they trust it. Is it enough? It's necessary. So these people trusting is necessary but not enough. Because then somewhere you may not trust and things may get broken. Now suppose, let's understand the trust mechanism. How do you trust? Whether somebody will trust a message or not, you cannot say a priori, right? Can you say a priori that I forward this message and this person will trust it or not? So the best way to model that is probability. So the best way to model trust with probability, let's call it P. Somebody asked a question? No. That's the best model we could come up with. Because trust is generally random. So trust with probability P. Now, what we want is the following. The question is, let's ask this question. P is a number. When is it full trust? P is 1. So we know at P equal to 1, it reaches everyone. When no trust, P equal to 0, we know it does not reach anyone. What happens in between? May or may not. Now let's ask this question little intuitively. Suppose at P equal to 0.25, I told you, suppose P is 0.25 and I told you that this information reaches to 90% of the people. Not everyone, but 90%. Fine? Is everybody got the question? P equal to 0.25, it reaches 90% of the people. Now I ask the following question. P equal to 0.3, at least how many people it will reach to? Is everybody okay with that intuition? Why do you think it's correct? You see, it's correct. I am telling it's correct. It's fine. That's a natural intuition to have. But any logical reason to believe why it should be? Yeah. Yeah, that's the intuition. But why? Why do you think? No, 100% I am saying, but why it can't be that, for example, why it can't be that, yeah, go ahead. More you send it forward. But it's all random, right? It's not deterministic. So cannot there be a scenario where I trust it more, but still something backfires? Very good. That's a very good point. So what it's saying is that there is a very interesting difference. So when I said it reaches 90% of the people, okay, so I'm not going to write this down because formally I cannot write this down. That gets a little tricky. I mean, I have to bring some probability notations. So I'll just talk intuitively. When I said with probability 0.25, it reaches 90% of the people. Is it always reaching 90% of the people? With probability 0.25, what will happen that maybe 99% of the time it will reach 90% people. So let's put it this way. This I can write, but not the very formal thing. So suppose P is 0.25. What will happen? Reaches 90% of people 95% of the time. So this is a very interesting, there are two numbers. One is it reaches 90% of the people, another is 95% of the time, not all the time. Now what does that mean? Let's understand. Let's understand this. Let's try to understand this with a simple graph. Okay. I'll draw a very simple looking graph. Just this, nothing else. Okay, let's try to understand it. Suppose this is the source of the information, like information, this person is connected to the teacher, or in this case, whatever, it gets the first forward, so the information goes here. Okay. Now, how many guys are there? 4, and let me put one more so that I can do 90%. 5, still it's not okay. Yeah. Or maybe I'll just put the number to 80% so that it's nice. Just for calculation. 5, 80% is nice, it becomes 4. 90% does not look nice. I just tweak, because otherwise I may have to make the network bigger. Okay, so this is the case. Now, to reach 80% of the people, how many people it should reach to? 4. So one guy already got it, I need 4 more. 3 more, sorry, 3 more. Very good. Now, how can it reach to 3 more? Is that this guy gets it? There are very different ways of having 4. So one approach is, suppose one is this guy gets it, but this guy does not trust it. So this trusts, this does not trust. This trusts, this does not trust. Then this guy trusts this, and then this guy also trusts this. This can happen, right? This is one way. We could have it in other way also, which I'll put with it orange. Is that this guy trusts, this guy does not trust. And then this guy trusts, and then this guy trusts. There are 2 different ways of having 4 people convinced or 80% convinced, right? But there are ways to having nobody convinced, like very few people convinced, much less than 80%. Let's see. So these 2 cases are 80% convinced, 80% reached. But there could be other way. Suppose I go with this, that where this guy trusts, this guy also trusts. So it looks like a better scenario. Both of them trust. But then, this guy does not trust, this guy does not trust. So to begin with, both trust, after that, nobody trusts. So this is another, it could happen this way also. So there are many possible ways. No. The trust is, do I trust the information? So it's like this person is sending me the information. Do I just delete the WhatsApp message or accept it? Yes. And then I try to forward.
So then in that case, the reason we have one person trusts the information, one person doesn't trust, then that person doesn't trust the information, we don't count them as having got the information.
Yes, exactly. Because it's like, if I don't trust, that means I think it's a spam. I won't do anything with it. I'll just drop it. Good? Yeah.
So what does the lowercase p denote? Does the 0.25 denote like the probability of one trusting the other person?
Yes. So this P is trust with probability P.
But it's not like it's really low, right?
It's really low. Yeah.
But then like even if it's really low, how is it reaching 80% of people? 95% of the time? Shouldn't the probability be higher to reach such a...
Very good. So we are trying to see in this case, does it reach 80% of the people 95% of the time? So to reach 80%, we figured out we need to reach total 4 people. What we figure out, there are different ways of reaching. So there are many possible ways. Now, what does that mean? So now we'll try to calculate 95% of the time. This question we have not figure out in this case whether I am reaching it 95% of the time. I have to now only figure out what are the possible ways to reach 80%. Now, the possible ways to reach 80%, does it happen 95% of the time? That's the next question we are going to ask. Fine? So what we have figured out, again let's repeat, as I said, there are 2 numbers. It's not reaching 80, first thing we get convinced, it's not reaching 80% of the people 100% of the time. That's not possible. Why? We saw there are these cases where it won't happen. Now the question is, does it reach 80% of the people 95% of the time or not? How do I figure it out? How do I answer this question? That this number of the time. What does that mean even? When we say 95% of the time something works, what does that mean?
100 instances, 95%. 95 instances,
Okay. What does it mean? Suppose I say my coin give head 50% of the time. What does that mean?
Number of trials increases the 50% of the times.
Very good. It simply means if I have a coin, suppose I told you this coin I give you, I tell you this is a fair coin, 50% of the time it will give head. What does it mean? It means if you toss many times, 100, 1000, roughly 50% of the time you will get head. Now apply that here. What does it mean? No, it's not the network increases. It's like, very good, very good. The instance here is the experiment is one message being sent. So, how would I decide that this method tried reaches to 80% of the people 95% of the time? It's like that will be known to the teacher. Suppose a senior teacher like madam who has been teaching for 30-40 years. She has done this many times. Suppose the date changed and she messaged to parents, then from parents it reached to other parents, from parents to other parents. She tried it many times and figured out that how many times it reaches 80% of the parents. She saw, maybe I tried the experiment in my life 500 times and maybe 400 times it reached to 80% of the parents. In that case, I'll say it reaches 80% of the parents 80% of the time. Right? So that's what it means by this second part. Of the time is nothing but try many times. So number of success by number of trials. And what is success in this case? Exactly. This is the success. Very good. So there are two numbers. Both are important.
So, can success also mean reaching above 80%?
Yes. So when we say reaches 80% of the people, we mean reaches more than equal to 80%. Means my benchmark is 80% people should know that this is happening. Okay. Good. Now we know the meaning of both the numbers. Now let's take one more step. What do we call if my coin toss comes head 50% of the time? We say, suppose my toss is head 80% of the time. It's a biased coin. But we call that 80% of the time coming head as probability of head. Right? Right? So this number of time, this success and this whole thing is actually also probability of success. Right? It's also probability of success. Fine, everyone is okay? Now that means if I can figure out the probability of reaching to 80% of the people, I am done. I would know whether it's 95% or 80% or 30%. Right? Everyone? Fine? Everyone with me so far? Now, how do I figure out the probability? How do I generally figure out probability? To figure out probability, I first have to write the outcomes of the experiments. What are the outcomes of this experiment? First, write down outcomes. And then for each outcome, I have to evaluate the probability of that outcome. What are the outcomes in this experiment? That's a very good question. That itself is a, how much time do I have? 10 minutes. 6 minutes. 15. Oh, 15. Okay. Oh, nice, interesting. I thought I was saying 6. Oh, you're using 2 hands for 2 digits. Nice. Okay. So, what are the outcomes? Let's see. The outcomes are the following. Let's look at these nodes. First thing, my outcomes will depend on who trusted, who did not trust, or who got the information, who did not get information. So, to say who got and who did not get, first I have to label the nodes. Label means I have to put a name. Okay. So, one way just to put a name A, B, C, D, E. So, we could just say this is A, this is B, this is C and so on. Or I could number it also. This is first 1, 2, 3, 4, whichever way you want to number. So, I could also say A1, B2, C is 3 and so on. And maybe this is D, D is 4 and this is E, E is 5. Okay. So, what are my outcomes? Outcomes are what is the state of A, B, C, D, E or what we call 1, 2, 3, 4, 5. What are the state of these nodes? That are my outcomes. Right? What could be the states of each of them individually? either I or cross. Right? Also it could be, right? Now one quick questions. This is part of your plus 2 syllabus. How many such outcomes? Why? Very good. So it's everything is 2. So there are total 2 power 5 possibilities. Yes. Oh, sorry. A is always I. So then what will happen? Right? Because I have always have, or you can also say it's 2 power 4 5 4. Because A is fixed. Sorry, yeah. I have other than A 4 guys. Yeah.
Now, if let's say one of them from A, one of them trusts it, one of them doesn't. The guy that trusts it passes the information to the other who trusts the information and then passes it back to the person who doesn't trust it. In that case, will the person still not trust it, or because he received that information, two people trust it? How does it look?
Yeah, so she trusts kind of, that's a very good question. So what he is asking is the following. It's a very good practical question. Let's saying that, suppose look at this guy C. It's getting information from 2 sources. Does he trust them? Like, does he trust the information? Like, this information is garbage? Or does he trust the person? So, you could think of both. There are both models. So, depending on the particular problem, you can model it differently. One is the source. Do I trust the source? If I trust the source, then I trust this friend versus this friend differently. So, I may trust this guy, may not trust this guy. But another thing, I don't even trust the source, the information itself. So, in that case, I don't trust either. So, there is a technical name for this. Okay. I won't get into that. I'll then talk to you at the end. Yeah, Arvind is smiling. So, I am kind of smuggling lot of stuff which don't even teach to our kids in 3rd year. So, but I am smuggling in a very simple way. So, I'll tell the names at the end so that you can go back and read about them. So, what I am trying to show you that if I don't use the terms, many of the time things are quite simple. As soon as you throw terms and throw notations, things look complicated. So, what I have already taught you is, I don't know, Arvind teaches in his course, at some point he needs for LDPC course, a little bit of it, but we are smuggling it now. Okay. But there's a very good question. What's your name? Huh? Parthasarathi. Parthiv. Okay. Parthiv. Okay. So Parthiv, a very good question. And whether you trust the persons or the information, that depends on the situation. It's like it depends on what your bias is. Suppose you are unbiased to the information. You are okay to receive any information, you just trust the source. Another thing could be, maybe suppose it's a political message. Okay, suppose a particular political party is spreading, but you are already biased against the party. Then it does not matter the source. Your father told you, or your brother told you, or your greatest enemy told you, does not matter. You don't trust it because you have already believe in something. So both are important. Here, let's stick to the model that we trust the source or don't trust the source, not necessarily the message. Okay. Message is neutral. I have nothing against the message. Fine? Now we have these outcomes and all these outcomes. Now how do I figure out probability of success? Can somebody tell me? I am saying you already know it.
So we should count the number of times we get 4 eyes.
4i. Very good. So what we'll have to do is look at outcome. Suppose I call it outcome 1, O1. O2, O3 and so on. Okay.
With 4 or 5 bytes, yes, should be at least.
Very good. So what I'll do here is check. Suppose put a probability of OI. I is the ith outcome. And I have to sum over all such outcomes which is success. What does that mean? Let's see it intuitively. Suppose I write it IXI, IX, so on. Who is success? Is this guy success? Is this guy success? Is this guy success? So how do I find probability of success? Look at all these outcomes which give me success, calculate each of their probabilities and add them. This summation simply means this. Take all the success and add this. So this notation everybody is familiar, right? This is a sum. So I am summing over all the outcomes which give me success. And the probability of those outcomes are summed up. Fine? Now the next question, which is, what is the big question now? Huh? But to get there, I need to, how do I get this probability? Did I even tell you, I only know the outcomes. But to calculate probability, huh? Very good. Now, how do I get to the case that probability of this? What is the probability of everybody's I? Now, this is getting interesting now. Very good.
So also some of the 32 outcomes won't be even possible.
See, now, this is very good. What's your name? Mukund. You? Huh? Aditya. So, what they said, both are very important. See, it's natural to ask, what's your name? Sorry? Sudhir. See, what Sudhir said, that's a natural approach. Okay, there are 16 outcomes total. So, maybe 1 by 16, each of them. It's fine. That is okay as long as all are equal. That's not 1 by 16 either. That's a good point. See, 1 by 16 would have been, there are 16 outcomes, each of them are likely. When it will be 1 by 16? Suppose I have 4 coins, all of them are bias half or like they are fair. I ask the question all head. That would be 1 by 16 because there is one case which is all head divided by 16 possible outcomes, 1 by 16. Now here they are not all same. How do I deal with that? How do I study that case where not all outcomes have the same probability? The answer is what they said, Mukund and Aditya. It will depend on the P and it will depend on the connections. Okay. So let's, whatever time I have, all of it we won't do, but yeah, 3 minutes, 5 minutes. Okay. What I'll do is, I'll quickly show, calculate some cases and see that just this equal counting is not the right approach all the time. Okay.
Based on the links in the graph, some of the outcomes may not even be possible.
That's a very good point. Which I also did not tell you is, suppose I give you this following thing. Let's look at this outcome since, forgot your name, sir. Parthiv, yes. So look at this and tell me, is the following outcome even possible? I tell you, this is A, B, C, right? Suppose I tell you I, X, X, I. Yeah. Is this even possible? Why? I. That means this is, got it, these two did not trust, but these two trust. If these two did not trust, how could go to these two guys? It's not even possible. Now then why did we put it in the outcome? The idea is, there are two ways of doing outcomes. You can actually add spurious outcomes which are not possible and make their probability 0. That's also okay. So what happens for certain, this is a counting problem on a graph. Sometimes they are adding some spurious outcomes which are not possible. Add them to your set, but you calculate the probabilities in a clever way so that it always stays 0. So that helps with certain counting issues. Okay. So you can do that. That's okay. As long as you don't put any probability on them. Fine? Is everybody okay with this? You can always extend your set of outcomes, but whatever you extend, spurious guys, make sure they're 0 probability. That does not affect your probability calculations in any way. Because something not in the outcome space or something having probability 0 in the outcome space has same impact on your calculation of final probability. Okay. But by the way, in your plus 2 you won't have to use this trick. I don't think it will ever show up, but this is a standard trick in when problems get complicated, people do that. Okay. Now, let's look at one particular case which is A, B, C, D, E, where everybody is I. And let's call this outcome O1. And I am to ask the question probability O1. How do I calculate it? How do I get it? Let's draw the picture. So this is something, we'll stop here. This is already outside your scope of syllabus, but we can do it. So let's do it. Do you have a line between them? Yes. The graph should always match. So A, B, D, C, E. Yes. So every here is P. And P is my 1 by 4 or 0.25, whatever. But we'll try to get the now thing in terms of P so that you can plug in any P and get the result. Now let's see a physical mechanism. How would it spread to everyone? First is this guy gets it. This guy gets it with probability 1 because it's the first guy to get. After that, it can happen that both trust, this is one approach. Then this will get I and I. Then it could be these two also trust, like this person trusts both of them and becomes I. And then this person also trusts both of them, becomes I. Okay, that's one approach. Another approach is this trust, and now this guy could get it, this got. Now this guy here could get it either from him or from him. And then suppose I say this trust but this does not trust. And this does not trust, this trust. Shall I still be all I? Any other things you can think of? Let me go for another color. This trust, this does not trust. But this trust, this does not trust. Now this trust. So what's happening? It's going in a different way physically. It goes to this guy, then it goes to this guy, then it kind of comes back to this guy because it does not trust either of this. Then this guy may be trusting him and not him. Now we could write many such ways, right? Trust, don't trust. You could write many such combinations. Can I urge you to think of all those combinations? When you go back, think about all these ways of getting it. Now after this happens, there are only one thing to calculate. What is that? Very good. So now what I need, suppose I look at the green guy. So the green path. What do you have to calculate? This is yes, this is yes, this is no, this is no, this is yes, this is yes, this is no. So what is actually happening here? It's like I have the edges. What are they? They are my edges. And what I am questioning, suppose I number these edges. Suppose I call this edge as E1, E2, E3, E4, E5, E6, E7. So, I could say this green path is nothing but E1 is 1, E2 0, E3 0, E4 1, E5 1, E6 0, E7 1. Why? So instead of 1, you could also call 1 is actually tick and 0 is actually cross. So you can also. I am just replacing tick by 1 and cross by 0. So you could also say that the green path is nothing but this, a property of the connections. Is it a trusty connections or not trusty? Okay? Now, after this happens, our problem becomes simpler. So, asking probability O1 is actually nothing but probability of orange path plus probability of green path plus probability of red path and few more terms which I ask you to figure it out. Now what I am doing here, I am trying to figure out probability of each of this path. Now what I have shown that this path is equivalent to this edges taking 1 or 0, tick or cross. Now why is this is an easier problem? Like why can I solve from now?
So if it's 1, we multiply by t. If it is 0, we multiply by 1 minus t.
Exactly. So this is something Keshav had taught you because now they are because I am tossing I am kind of choosing them to be correct or not, trust or not trust with probability P, which is like tossing a coin with probability P and getting a head with probability P. Now, what is the probability that this is head, this is head, this is tail, this is tail, this is head, this is head, this is tail, this is head? Is like P times 1 minus P times 1 minus P times P. Right? So now you write it down, all of them, and calculate. You will get an expression in terms of P. And that will be a probability of all I. After that, you have to look at cases with 4 or more I's. 5 I's is this. After that, look for all 4 I's. Fine? And keep adding. Okay? So this is where we are doing is a problem that looked complicated on a graph, how it spreads. We have boiled it down to just coin tosses, 7 coin tosses. All of them are independent coin tosses. So generally all of advanced math, any advanced math is actually that. I can vouch for probability. You will learn about something called 3 axioms of probability when you go to your +2. And then after that, all of machine learning, all of information theory, whatever you can think of, they are always a way to see that big problem and go step by step and boil down to those 3 axioms. So if something is big, they must have a root in the small thing, what you learn. So here, from this big problem, we went down to simple coin toss. And that's all math problem is that. Okay, yeah, go ahead, Parthiv.
There should be an easier way to calculate this probability, because all we need is, for one person, all we need is one trustworthy expert.
Very good.
For the information research. So then it doesn't matter when all the other edges are crosses. So then we can simply say the probability of each of all of them having one trustworthy edge, 0.25 to the power 4. That should be total probability of all edges.
There is a so what will happen is, because the order also matters, as we saw this case, right? Suppose I tell these are all positive, right? So if I just look at this guy and say what's happening here, that this edge is open, this edge is tick, this is tick, this is tick, but these two are cross, then nothing reaches, despite that. So the probability of this open and this open will be p square, but since these are not reaching anywhere, we will never reach 4 guys. So you have to be little careful with that also. So generally what happens for a really big graph, the approach I took, it's a very simplified approach, it won't work. There is another approach which will work. This case I can do by hand calculation, but think of a social network of million nodes. I can't do hand calculation. So this won't work. But a similar intuition which we can build from here will work. So that I won't go there. This is good enough to see how it can be transformed from information to this edge, and which is multiple coin tosses. But for bigger graphs, this approach will be, it's not that it won't work, it won't be scalable, it's not easy to calculate. Okay. So whatever we did today, this whole thing is as a name, it's called percolation. And if you want to know more about it, you should talk to Keshav, Professor Keshav. He works on this. This is his bread and butter. We also do little bit, but he works on it all the time. And remember this 2 things that Parthiv asked, whether I trust the source or trust the information. And they have a particular name. When I trust the source individually, separately, that is called bond percolation. And when I trust the news or not as a whole, that's called site percolation. So you can search about it. read about it, and the main thing is we will see that there is a value of P. So P being more than some number, P hat, it will reach 80% of the people 90% of time. And if P is less than P hat, this won't happen. And this is called percolation threshold. This is called percolation threshold. So that means my P has to be sufficiently big to reach to everyone. If it's very small, it may not reach. So, done? Okay. You got this chalk or who got? This is not the IIT chalk, this is very different. No, madam didn't. This because this is a different chalk, maybe we can recommend to IIT because the color variety is much better. Boards are good. These boards are quite good. So this is something I ended with this just to tell you if you want to search and read about it on Wikipedia or Google or whatever, what to search for. So we kind of smuggled in a bit of percolation without taking the name, but at the end only I took the name. Okay. Okay, so the motivation was social networks, but the motivation works in many other cases. Like, suppose a computer virus is spreading. You know, heard of computer virus? Not only that, a human virus is spreading. It's like, I have some infection, viral fever. Like, few weeks back, I think last week, Harini had. So I don't know how many of will get it through percolation. Because the way infection spread is percolation. Like, she is sitting next to whom? That's her graph, like these two girls. They are her graph. Whether they get it or not, that probability P. You know what is that P? That's the individual immunity level of the girls. How immune they are. Do you have good immunity or not? And based on that, you can calculate how many people among you will get it. Okay. So, it applies in many cases. Okay.
I would like to sincerely thank Professor Avishek Chaterjee for today's engaging lecture on influence networks and probability-based models. The way you explain how information spreads, how individuals influence one another, and how probability helps predict outcomes made the session extremely interesting and easy to follow. Thank you for sharing your valuable knowledge and insights with us. We truly enjoyed and learned a lot from this session. Thank you so much, sir.